All right, hey class. We're going to go over lecture 26 now, just kind of cruising right along. We've learned about some of the different solution properties, or sorry, we've learned about solutions and concentration. Today we're going to be learning about some of the properties of those solutions. So go ahead and get started here. Okay. So go ahead and try this quiz question on your own as kind of a review. Okay, so the question says, how many grams of zinc are used up when it reacts with 75 milliliters of a 4 molar HCl solution? All right, so how many grams of zinc are used up? Okay, so here we're going to be going from volume of A to moles of A over to moles of B, and then to grams of B. And this is volume of A of a solution, right? Okay, so A in this case is going to be our hydrochloric acid, and then zinc would be our B. So we're starting with volume of A, so 75 milliliters HCl. And we need to go from volume of A to moles of A using the molarity. So I'm just going to quickly convert the milliliters to liters, and then use the molarity, which is 4.00 moles of HCl for every 1 liter of solution. Okay, sorry, this isn't HCl, this is actually 75 milliliters of solution. Okay. And then we can convert from moles of HCl over to moles of zinc using the chemical equation. And then using the molar mass of Z, we can say the molar mass of zinc. Say 1 mole of zinc is a certain number of grams of zinc. I don't know the molar mass off the top of my head. Molar mass is 65.4. Cool. All right, and that will pop out the grams of zinc. So hopefully that's some review that you were able to practice on during the homework. All right, here's a good quiz question. And you don't need to like pause it and answer this, but think about this. Does water boil faster if you add salt to it? You might have heard this before, like you're cooking pasta or something and somebody puts salt in it. And like, why'd you put salt in it? Like, oh, it boils faster. So we're going to talk about some properties of solutions today and answer this question, right? Does water boil faster if you add salt to it? Okay, we'll keep you in suspense. All right, colligative properties. Okay, so this is kind of just a definition term. Colligative properties refers to the properties of a solvent that change when solute particles are added. So like if you have a cup of water and you added salt to it, what does that change as far as the properties go? Those are colligative properties, things that change when you add salt to it. And these properties depend on the number of solute particles. That's it, just the number. It doesn't matter what the solute particles are. Okay, just depends simply on the number of solute particles. So as an example, and we'll talk about this more, but adding salt or any kind of solute to water is going to lower the freezing point and it's going to increase the boiling point. Okay. Okay. So, sorry, before we move on, kind of answering the question, we're going to talk about why, but it does increase the boiling point. So if you think about the example before where we add salt to water, does that help water boil faster? The reality is no, it actually would take longer because if you add salt to water, you increase the boiling point of that water, okay? So it actually would take longer because the boiling point is higher. So it's going to take longer for that water to boil. The reason you add salt, there is some benefit to adding salt to water, right, is you increase the boiling point of the water. And so if you're cooking, let's say you're at sea level and you're cooking pasta in water that's boiling, and your pasta is cooking at 100 degrees Celsius. If you add salt to that water, then that raises the boiling point. And so maybe it depends on how much salt you add. We'll see an example here in a second. But let's say you added enough salt to where you increase the boiling point of the water up to 105 degrees Celsius. Now you're cooking pasta at 105 degrees Celsius. And so the pasta should cook faster because it's getting hotter. So it's not that the water boils faster, but that the pasta would actually cook quicker. We're going to go through an example and see how much of a difference adding salt really makes when you're cooking though. Okay. So if you add 1 mole of solute particles to 1 kilogram of water, the freezing point of water decreases by 1.86 degrees Celsius. This is just an experimental thing, right? So you're going to go over a couple like numbers, constants here, and these are just determined experimentally. So the scientists put 1 mole of solute particles in water, and notice that the freezing point actually went down by 1.86 degrees Celsius, and the boiling point increased by 0.52 degrees Celsius. Okay. So these numbers are known as K sub F and K sub B. Okay. And so again, this is how the numbers were determined. And the equation that you're going to use to figure out how much the temperature changes, because we're not always going to be dealing with 1 mole of solute particles in 1 kilogram of water. Okay. So this equation allows you to figure out what's the change in temperature given any number of moles of solute and any mass of water that we're using. So the top number is going to be in terms of moles and the bottom is in terms of kilograms. The way to remember that is just to look at the constant itself, and you'll see that you're dealing with temperature in Celsius, mass in kilograms, and moles in moles. Okay. All right. So let's talk about why this happens, why the boiling point increases and the freezing point decreases. So if you look at this graph here, this orange line represents pure water, okay? So this would be water. So this is basically the freezing point of water, so that's 0 degrees Celsius. And this right here would be the boiling point of water, which is 100 degrees Celsius. When you add solutes to water, it actually lowers the vapor pressure, right? Because not as much water is going to be moving into the gas phase if you add solute in there. By lowering the vapor pressure, this line becomes lower, and you can see that in order to get it to 1 atmosphere of pressure, again, water boils when the vapor pressure equals the atmospheric pressure. So if the atmospheric pressure is 1, because we've lowered the vapor pressure, you're going to need to add more temperature in order to get that water to boil. So this is going to be something greater than 100 degrees Celsius, right? And when you also, by lowering that vapor pressure, you see vapor pressures here on the left side, you lower that line, then the freezing point, so this phase between liquid and solid, is also lowered. You can see that there. So this would be less than 100, or sorry, less than 0 degrees Celsius. Okay. You don't need to be like able to produce this graph. This is just kind of a visual to see what's going on. The main idea I want you to know is that by adding solutes, you raise the boiling point and you lower the freezing point. So you make that window of liquid bigger, okay? All right. So before moving on, I'm just going to talk about some interesting applications of this, okay? So in the last example, and these are, again, just interesting applications. You don't need to like take notes on this or anything. So 1 mole of solute particles. So we talked about adding salt to water to see how that would make pasta cook faster, right? So let's say you have 1 kilogram of water. 1 kilogram of water is 1 liter of water, which if you think in terms, I always think of like a 2 liter like soda bottle or whatever. That helps me visualize what 1 liter is. So I could see like if I'm cooking pasta using 1 liter of water, right? So in order to make, if I'm using 1 liter of water, if I added 1 mole of solute particles, okay, 1 mole of sodium chloride is 58.5 grams of sodium chloride. That's a lot, right? That's not like a pinch. That's like probably, I don't know, I would imagine at least like a quarter or a half a cup maybe of sodium chloride that you'd have to add into that 1 liter. Adding that much salt would raise the boiling point by 0.5 degrees Celsius. So I mentioned that adding salt, it doesn't help the water boil faster, but it does cook the pasta at a higher temperature. That being said, you would have to add so much salt to make this number significant that, I mean, you're not going to do it because your food would be really salty. Which maybe you like, I don't know. But anyway, most people add like a pinch of salt, right, in the water, and they say it's going to cook faster. And it's like, well, you're really increasing the boiling point by like 0.01 degree. It's not going to make that much of a difference. The time it took for you to put the salt in is going to be more than the time you gain cooking the pasta. Anyway, just some fun things, right? The other thing I like to point out here is when people salt ice on the road, okay? So let's say this is your liquid phase of water is going to be between 0 degrees and 100 degrees Celsius, right? If I add salt to something, that temperature is going to go up. Let's say I add enough salt to make the temperature go up 10 degrees. So now our new boiling point is 110, and our freezing point is maybe negative 20 degrees Celsius or something, okay? So when you have ice on the roads, it's probably, I don't know, let's say it's like negative 10 degrees outside, okay? So the outside temperature is negative 10 degrees Celsius. So if the outside temperature is negative 10 degrees Celsius and you have pure water on the road, then all that water is going to be ice, right? Because anything lower than 0 degrees, any temperature lower than 0 degrees would freeze the water. But if you add salt to that, then you've actually expanded the liquid phase of water to include negative 10 degrees Celsius. So now any of the ice that you have, if it's mixed with that salt, the freezing point of that is actually maybe negative 20, right? These are just numbers I'm throwing out. But it lowers the freezing point so that the ice is now in liquid form even when it's negative 10 degrees Celsius outside. So that's kind of the principle behind adding salt to ice to melt it. Anyway, all right. Again, you don't really need to know those things. It's just kind of for fun. All right, let's go ahead and try this question here. See if you can answer it. Okay, so it says, what happens if we add 1 mole of calcium chloride to 1 kilogram of water? What is the freezing point? Okay, so if we write out the equation for calcium chloride, right, once this is put into water, it's going to separate into calcium ions and chloride ions. So by adding 1 mole of calcium chloride, we actually add 3 moles of ions, right? Because we get 1 mole of calcium out of it, and we get 2 moles of chloride ions out of it. So 3 moles of ions total. Okay, so our delta T is going to be K, which is this number right here. Right? This is KF because we're talking about the freezing point. That's what the F is for. And then you have the moles of solute, which is the moles of the ions, over the mass of the water, which we have 1 kilogram of water. So run that calculation out. It's going to tell us that the temperature is going to decrease by negative 5.58 degrees Celsius. The original freezing point of water is 0, so 0 minus the 5.58 is just negative 5.58 degrees Celsius is the new freezing point for that water, or for that aqueous solution. All right, cool. Go ahead and try this one as well. We're talking about boiling point here. Okay, so this question says, what is the boiling point of water if you add 117 grams of sodium chloride to 250 grams of water? So in order to use the equation here, we need Kb for the boiling point, which we already have. We need the moles of solute, which we aren't really given in the problem, and we need mass of water in terms of kilograms. We have mass of water in grams here, so we pretty much have this one. So to get the moles of solute, right, we're converting from grams of sodium chloride to moles. We're going to use the molar mass. So you can take 117 grams sodium chloride, and then we'll use the molar mass of sodium chloride over 1 mole. Okay, and that would give you the moles of sodium chloride that you add. Okay, so you could do that calculation separately, or you can, so you do that separation, or sorry, that calculation separately. Let me do it real quick on a calculator. See if I can back this out real quick. Oh, darn it. Okay. So I had 117 grams sodium chloride. For converting grams to moles, we divide by 58.5 grams of sodium chloride for every 1 mole of sodium chloride. Should be 2, yeah. Okay, so that would give me 2 moles of sodium chloride. Okay. Now, if we looked at what happens to sodium chloride when it's placed in water, it's going to split up to sodium and chloride ions, right? So 2 moles of sodium chloride would actually equal 4 moles of ions. Okay. And another way to look at it is what the PowerPoint has here, where we say 1 mole of sodium chloride gives us 2 moles of ions, using like a conversion factor. Tells us that we have 4.0 moles of solute ions. Okay, so now that we have N, we can just put it in our equation. We convert the grams of water into kilograms, and we can use Kb here, right? And then we have the moles of solute over the mass of water in kilograms, and we can see that the temperature, the boiling point, goes up by 8.32. The original boiling point of water is 100. You add the 8.32, and your new boiling point is 108.32 degrees Celsius. Okay. Awesome. Okay. So here's an interesting quiz question. Go ahead and pause it and try and answer this and see how you're doing with this. Okay. So the question says, which of the following would have the lowest freezing point, right? So we're looking for the largest delta T. We've talked about how delta T equals K, in this case Kf, times the moles of solute over the mass of water, right? Well, in all 3 of these, we have 100 grams of water. Oh, sorry, in D, we have 100 grams of water as well. The freezing point goes down if we add solute. So that already eliminates D, right? Because any of these is going to make the freezing point go lower than the freezing point of just pure water. In A, we're adding 0.1 moles of sugar, right? And sugar is, if you put it in water, it's just going to be sugar still. So this one would give you 0.10 moles of solute. Sodium chloride, if that was placed in water, it would dissolve into sodium plus ions and chloride ions. So that would actually produce 2 times as many moles. So that would give us 0.20 moles of ions or solute. Okay. And then 0.1 moles of calcium chloride. Okay, calcium chloride would dissolve into calcium 2 plus and 2 chloride ions. So that would give us actually 3 times as many, right? Okay. So if C gives us the highest number of moles of solute, which means it would give us the largest delta T, right? So it would lower the freezing point by the most amount. Okay. Okay, our last concept in this lecture is going to be that of osmosis. You may have heard of before. But basically in osmosis, what's happening is water is going to move to try and create a equilibrium of concentration. So you have a semi-permeable membrane, which allows water to move through, but the sucrose particles here cannot move through, okay? So water flows from the lower solute concentration into the higher solute concentration, okay? So this is the lower concentration, obviously. There's not even solute, so water is going to be moving net. The net movement of water is towards the right side. So you can see how the level of water goes up versus the left side. And that driving force is the concentration. The water is trying to create an equilibrium of concentration, okay? Okay, yeah, so the level of solution with the higher solute concentration rises, and the two concentrations become equal with time, right? That's the goal. And then this, you might hear this term osmotic pressure, and that arises because of the difference in height. So you can imagine if there's more water on this side, it's exerting more pressure against this membrane than on the left side. And that's where the pressure comes from. So here's kind of a visual. If you have 4% starch versus 10%, right, you're trying to make the concentration more equal. In order to do that, water is going to move from the less concentrated to the more concentrated. Because if you add more water to the more concentrated, it's going to dilute this, and it's going to drive the concentration down a little bit. And as the water leaves the left side, it's going to concentrate it and drive the concentration of the left side up a little bit. So that's going to happen until you reach this equilibrium where you have 7% starch on both sides of the membrane. To do that, though, water moved to the right side, right? So the level of water rises on the side with the higher concentration, and it goes, or sorry, with the higher concentration initially, and then the water level goes down on the side with the lower concentration initially. And then this pressure that's being exerted now on this membrane versus the pressure on this side, because the water's lower, is your osmotic pressure that's going on. Okay, so we're going to apply this a little bit to red blood cells in a couple health applications that I think are interesting. Okay, so water can flow through cell walls, right? Not all particles can, but water can. So proteins, sugars, and ions cannot flow through the cell walls. Again, this is kind of as a caveat. There are certain transport proteins, right, that can send them across cell walls, but we're going to ignore those just for the purpose of for simplicity. Okay, so osmosis is important for blood cells. We're going to talk about 3 different kind of situations that a red blood cell can be in. One is an isotonic solution. So that's where the fluid surrounding the red blood cell, whatever it is has the same concentration as the concentration inside the red blood cell. That happens, it's called an isotonic, right? It's the same osmotic pressure. And because of that, there is zero net movement of water across the membrane. And so the red blood cell basically is unaffected, okay? The other situations where you have a hypotonic solution, that's where the concentration, hypo, right? We know that means like lower. Hyper is upper, hypo is lower. So that's where the solution has a lower osmotic pressure, okay? Lower concentration, right? Hypo is lower. And water, because there's a lower concentration on the outside, the water is going to flow into the red blood cell, right? So this causes swelling of the red blood cell. Hemolysis is the technical term, I guess. All right, and then the third situation is the hypertonic solution, which is the opposite of the last one, where we have a higher concentration on the outside. This is going to cause water to come outside of the cell, right, through osmosis, and the cell actually shrinks, and it's called crenation. Okay, so for these three ideas, what I really want you to know is like what would happen if a red blood cell was placed in a hypertonic solution. Okay, and really just understanding the principle of osmosis should help you there, right? So I could ask what happens in an isotonic solution, or a hypotonic solution, or a hypertonic solution. Okay. Then the last application, which don't worry about taking notes or anything on this. This is just kind of interesting. You've probably heard of dialysis, which works through osmosis. So what would happen is you have this, again, semi-permeable membrane on it, like it's an artificial membrane where small particles can pass out. Small waste particles like urea are passed from the blood outside, and then the large, more proteins and stuff are retained inside. What this looks like in real life is like a dialysis machine. You have blood from a patient coming into the machine. You have these small waste urea particles, right? This is if somebody's kidney isn't functioning correctly. So you pass it through this tube that has a semi-permeable membrane. Through osmosis, the waste particles actually move outside, right? They move out because they're trying to create a similar concentration as to what's inside. So in this example, you wouldn't necessarily have water moving in and out, but you'd have the urea or other waste products moving out to try and equalize the concentration. And as long as you're then getting rid of those particles and the blood keeps cycling through, after a while, you're going to have a lot of waste products removed, okay? Those waste products are removed, and then the clean blood is passed back into the patient, right? This is generally the job of the kidneys, but in dialysis, it's going to be a machine that's doing this job. So anyway, just kind of an interesting application. Don't need to know that specifically for the exam or anything. All right, hopefully that was helpful, and go ahead and work on the homework and keep practicing the solutions. I don't think that lecture had too many new ideas as compared to the last one, but you should be understanding how boiling points and freezing points can change based on the solution and the number of solutes, or in the case of like an ionic compound, the number of ions that are present, and then know the difference, understand osmosis and know the difference between isotonic, hypotonic, and hypertonic solutions. All right, that's it for this one. We'll catch you next time.